Across the ancient world, circular depressions in the Earth's surface were rarely understood as the result of celestial impacts. The concept of an object from space striking the Earth was beyond the available intellectual framework of nearly all early civilizations. In recorded sources from Mesopotamia, the Mediterranean, East Asia, Mesoamerica, and the Pacific, there are no descriptions that definitively interpret a depression or crater as the result of an extraterrestrial object. Instead, natural craters were interpreted through myth, theology, or symbolic geography. In most cases, they were absorbed into a sacred landscape and given religious or legendary significance. Large impact craters are uncommon, and many are located in geologically inactive or remote areas. Others are eroded beyond recognition. Most ancient populations lived far from obvious impact sites and lacked tools or theories to identify them as such. Without a concept of high-velocity, extraterrestrial collisions, these features were explained through existing belief systems. Volcanic craters were interpreted as divine forges, underworld gateways, or scars from battles between gods. Depressions were used as ritual sites or labeled as cursed ground. Their roundness, isolation, or association with water often gave them symbolic significance. No written or oral traditions from the period identify these as caused by falling objects from space. Visual phenomena like meteors, comets, and fireballs were widely observed and systematically interpreted, but not materially linked to ground features. Cultures tracked these events closely, often in religious or political contexts, and treated them as omens rather than physical processes. The idea that what appeared in the sky could strike the ground with force was not developed. Some societies recorded detailed meteor activity, including the Mesopotamians, Chinese, and Mesoamericans, but their interpretations remained within symbolic frameworks. Meteors signaled the death of kings, divine anger, or the rise of new powers. The separation between celestial signs and geological consequences remained total. No evidence indicates that any pre-modern society connected a specific meteor with a ground impact. It lacked the means to do so. Craters were real, meteors were observed, but their relationship remained unrecognized. The concept of a meteorite impact crater would not emerge until modern geology and astronomy developed the tools to link the two. In ancient Mesopotamia, events in the sky were considered expressions of divine will. Celestial bodies, including meteors and comets, were categorized and recorded in cuneiform omen texts like the Enuma Anu Enlil, compiled over centuries from at least the 2nd millennium BCE, when a meteor appeared. The court scholars interpreted its trajectory, brightness, and direction. A meteor that crossed the sky from west to east could indicate the defeat of Western armies. If it disappeared behind a specific constellation, it might mean that a king's reign would end. Each interpretation depended on a fixed set of associations. Between astronomical phenomena and political outcomes, meteors were not understood as physical objects. They were signs immediate and urgent. In Assyrian and Babylonian texts, when a meteor appeared on a night when the moon was obscured, the king was warned of rebellion. Priests performed appeasement rituals to avert disaster. These rituals had no relation to the object's origin or trajectory. Their function was symbolic correction. The concern was not what the object was, but what it meant. Comets were treated similarly. Their drawn-out appearance across the sky made them especially threatening. Interpreted as long-term warnings of disease, famine, or dynastic collapse. In China, the tracking of meteors and comets was assigned to court astronomers, who compiled detailed celestial records spanning thousands of years. As early as the Warring States period, state-sponsored observers monitored the night sky for anomalies. When a bright meteor or fireball was observed, officials consulted existing interpretive texts such as the Tianwenlu. If the meteor was large or noisy, it might indicate military defeat. If it appeared near the time of a solar eclipse, it could mean the fall of a ruler. Like in Mesopotamia, failure to detect or properly interpret these signs could result in punishment or execution. Some Chinese sources reference falling stones, and there are isolated reports of meteorites reaching the ground. However, the prevailing interpretation remains symbolic. The cosmos was seen as a self-regulating order, and any irregularity was an imbalance. A meteor was not a space rock, it was a rupture in that balance. It demanded ritual correction, and often changes in court behavior or state ritual. And Roman interpretations blended superstition with philosophical speculation. While thinkers like Aristotle rejected the idea that celestial bodies could change or decay, exceptions were made for comets and meteors. These were sometimes believed to exist below the sphere of the moon, and thus could be interpreted as atmospheric phenomena. However, this did not lead to a physical understanding of impact. Instead, it reinforced the idea that meteors were fiery vapors or sublunary omens. The Stoics and Platonists debated the permanence of stars, but largely ignored meteoric activity as physical intrusion. Roman authors recorded multiple examples of meteors and comets being linked to death and upheaval. According to Livy, a comet was observed before the assassination of Julius Caesar. Suetonius wrote that a comet appeared during Caesar's funeral games, interpreted as a sign of his deification. In neither case was the object analyzed materially. The response was cultural. Coins were minted showing the comet as a divine star. It became a symbol rather than an object. Comets received similar treatment across other ancient societies. Mesoamerica. The Aztecs described smoking stars in codices like the Codex Telluriano-Amensis and Florentine Codex. These were depicted as portents of doom. In the years leading up to the Spanish conquest, fireballs and comets were recorded as signs of approaching catastrophe. Some chroniclers, writing after the conquest, retroactively connected these phenomena to the arrival of the Spaniards. Appearance of a comet or meteor, especially if followed by a natural disaster, reinforced the belief in divine prophecy. These interpretations were reinforced by cultural repetition. When a celestial event coincided with disease, flood, or political instability, it was not seen as coincidence, but confirmation. The appearance of Halley's Comet in 87 BCE was followed by wars and upheavals across the eastern Mediterranean. Later centuries, chroniclers often retrofitted comet sightings into the timeline of disasters. The object itself remained unexplained. It was the pattern that mattered. In North America, oral traditions from the Ojibwe and Lakota include stories of star beings and falling stars as manifestations of spiritual activity. Meteors were not seen as threats, but as connections to other realms. The Pony associated certain meteor paths with spiritual journeys, or ancestors crossing between worlds. Among some groups, fallen stones were kept as sacred items. However, these interpretations did not explore the object's origin or composition. The meaning was always derived from the object's movement and context, not its nature. In Polynesian traditions, fireballs and meteors were associated with navigation, death, or spiritual communication. Among the Emboria, a meteor might be interpreted as an atua, a god in transit, or as a spirit canoe. These interpretations were consistent and codified, often aligned with specific events such as funerals or births. Again, there was no known attempt to explain these objects through mechanical or astronomical principles. Across all of these traditions, the common pattern was interpretive separation. The sky was watched closely. Events were recorded. Responses were systematized. But the objects themselves were not examined as physical entities with mass, speed, or impact potential. A meteor might kill a king, a comet might signal war, but their nature was abstracted. The visible event was always filtered through a cosmological system. The failure to develop a physical model of meteors or comets was not due to lack of intelligence, but a lack of instrumentation and supporting theory. With no framework for gravity, orbital mechanics, or interplanetary matter, there was no reason to connect sky events with terrestrial geology. A crater was a volcano. A meteor was a sign. A comet was a tale of disaster. The events were real, but their meanings were system-dependent. Each culture built a consistent internal logic, but none escaped symbolic interpretation. Only centuries later, with the development of modern astronomy, would these events be reconsidered as evidence-based physical phenomena? The separation between sign and substance would eventually collapse, but not before thousands of years of records were generated, all designed to answer questions that never asked what the object was, only what it meant. In most ancient societies, a falling star was treated as a sign. But in rare cases, when a meteorite was recovered from the ground, it became an object of reverence. These were not studied for composition or origin. Instead, they were used ritually, displayed symbolically, or embedded in cultural myths. The common trait was their otherness. Their arrival was not reproducible. They were not quarried, traded, or smelted like normal stone or metal were found. That alone gave them power. One of the oldest known uses of meteoritic material comes from pre-dynastic Egypt. Artifacts dating to around 3200 BCE include small iron beads hammered into thin shapes. These beads have high nickel content and crystalline structures consistent with meteorites. Smelting iron from ore was not yet developed in Egypt. The iron in these objects was likely collected from small iron meteorites and cold-worked by hand. This early use predates the Egyptian Iron Age by more than a millennium. The material was not industrial, it was symbolic. Iron from the sky had ritual value. This tradition persisted. In the tomb of Tutankhamun, a dagger was found with a blade made of meteoritic iron. Its high nickel and cobalt content was confirmed in 2016 through X-ray fluorescence spectroscopy. No Egyptian smelting technique of the time could account for these levels. The blade was forged from meteoritic metal, probably sourced from a known strewn field. The craftsmanship is advanced, suggesting knowledge of how to work the material. Despite its rarity, the dagger was placed beside the Boy King as a high-status object. Its origin, a material that fell from the sky, made it appropriate for a ruler identified with the divine. In other cultures, meteorites were not shaped, but preserved in their original form. Among the Inuit of northwest Greenland, the Cape York meteorite provided a long-term source of iron. The largest fragment, called Anagito, weighs over 30 metric tons. Its presence was known to Inuit communities for centuries. The use stone, tools to extract flakes from exposed sections and fashion them into blades and harpoon tips. This use of meteoritic iron was functionally advanced, allowing for harder tools than those made from bone or stone. When Western explorers removed Anagito and other fragments in the 19th century, local accounts described the act as theft. The meteorite was not just a source of metal, it was a known and culturally important object in pre-Islamic Arabia. The black stone, embedded in the Kaaba in Mecca, has long been claimed by some scholars to be a meteorite. The stone is a dark, roughly egg-shaped object, now cracked and held together by a silver frame. Islamic tradition holds that it fell from the heavens and was placed in the Kaaba by the Prophet Ibrahim. Its religious role predates Islam, although its meteoritic origin remains uncertain due to restrictions on physical testing. The theory persists because of its shape, composition, and cultural framing. It is treated as a relic from beyond Earth, venerated by millions of pilgrims annually. Its impact is not in what it is scientifically, but in how it functions within religious identity. Other meteorites have been incorporated into ceremonial life in less visible ways. In Tibet, some ritual knives known as furba have been claimed to be made from sky iron. In these cases, the connection to meteoritic material is often unverifiable, but the belief in a celestial origin is central to their ritual purpose. The same is true in various African and oceanic cultures, where stones said to have fallen from the sky were preserved as sacred objects. These stones were not tools, they were displayed, worshipped, or hidden. The fact that they could not be traced to any known quarry reinforced their alien status. In ancient China, there are accounts of stones from heaven, especially during the Han Dynasty. While some may have been meteorites, others were likely unusual terrestrial rocks given symbolic meaning. The Chinese approach emphasized classification and pattern recognition over material analysis. A stone's fall was important, but its function was determined by divination. If a meteorite was found near a town struck by disaster, it might be buried or burned. In other cases, it might be offered to the emperor. The treatment depended on the reading of omens, not on empirical study. The idea of skystone technology, also appears in legends, such as the supposed weapons of the gods or kings forged from materials that came from the stars. In most cases, these are retroactive explanations for exceptional artifacts, harder metals, rare shapes, or mysterious origins. Without metallurgical testing, the belief in a celestial origin functioned as an explanation for anomaly. If something could not be explained by local geology or trade, it was said to have fallen. Meteorites that produced visible fireballs or left impact marks sometimes entered oral tradition. There are stories in both indigenous Australian and Native American communities of fire from the sky striking the ground, followed by the discovery of strange stones. These accounts often describe the meteorites as hot, glowing, or humming. The absence of a written record or scientific framework, the stories preserved a version of the event. In some cases, archaeological finds have matched locations described in oral accounts, supporting the idea that the events were real and the stones were preserved culturally. However, these examples are rare. The vast majority of meteorites likely went unnoticed or unrecognized. They do not resemble typical terrestrial rock. They are often dark, smooth, and unusually dense. In societies without iron technology, they may have been discarded as unusable. Only in cases where cultural meaning was already attached to celestial signs were meteorites retained and integrated into ritual life. The presence of meteoritic iron in elite burials, sacred buildings, and ceremonial tools shows that some ancient peoples engaged with these materials directly. But they did not study them scientifically. Their value was not derived from metallurgy or cosmochemistry, but from symbolic association. The sky was the source of authority, prophecy, and origin. The stone that came from it carried that authority into physical form. These stones were not just rare, they were meaningful, in every known case. Meteorites were used in ways consistent with existing belief systems. They were not disruptive discoveries. They were absorbed. Whether fashioned into tools, embedded in shrines, or left untouched, their function remained symbolic. Their significance did not depend on knowing what they were. It depended only on knowing where they came from. In the 5th century BCE, the Greek philosopher Anaxagoras proposed that celestial bodies were made of the same materials found on Earth. He stated that the sun was a fiery stone and that meteors were fragments that had broken off. This claim was based in part on a specific event. Around 467 BCE, a meteorite reportedly fell near Aegospotami in Thrace. Contemporary and later sources described it as a massive stone that descended during the day, accompanied by fire and noise. The object remained visible on the ground for generations and became the center of local veneration. Anaxagoras used this as evidence to challenge traditional cosmology. He rejected the divine nature of the heavens and argued instead for a mechanical universe governed by natural laws. His interpretation of meteors as falling rocks marked a conceptual shift. It was not broadly accepted. The dominant Greek model, based on Aristotelian physics, held that celestial bodies were incorruptible and fundamentally different from earthly matter. According to this view, change could only occur below the moon. Meteors and comets, therefore, were classified as atmospheric events, temporary phenomena resulting from exhalations or vapors in the upper air. This classification was not derived from observation of impact or material properties, but from the need to preserve the idea of celestial perfection. The distinction between the terrestrial and celestial realms remained in place throughout the Hellenistic and Roman periods. Even though Roman authors documented numerous meteor sightings, their explanations remained symbolic or atmospheric. Pliny the Elder, writing in the 1st century CE, described meteors and thunderstones, but did not associate them with impact craters or interplanetary motion. He reported that a meteorite had fallen in the reign of Emperor Nero, and that it was considered a religious sign. The stone was displayed, but not studied. The material explanation proposed by Anaxagoras did not re-enter serious philosophical discussion until the scientific revolution. Some thinkers during the Islamic Golden Age preserved and commented on Greek texts, including those of Anaxagoras. Scholars such as Avicenna and al-Biruni discussed meteors and comets, usually within the framework of Aristotelian cosmology. In general, they accepted that meteors were produced in the upper atmosphere by the interaction of dry exhalations and fire. These models were consistent with prevailing theories of natural motion and the four-element system. They did not posit that meteors were physical rocks moving through space. The idea that an object could enter Earth's atmosphere from beyond and strike the surface remained outside the dominant intellectual framework. The lack of a unifying theory of gravity or motion prevented progress, without an understanding of inertia, acceleration, or elliptical orbits. It was difficult to explain how a rock could fall from the sky without being a part of it. Comets, too, were subject to speculation, but not material analysis. Their long tails and sudden appearance made them difficult to classify. Aristotle believed they were sublunary phenomena, temporary fire created in the upper atmosphere. This view was widely accepted into the early modern period. In medieval Europe, meteors and comets were routinely included in chronicles as portents. Authors such as Matthew Paris and the Anglo-Saxon Chronicle noted their appearance in connection with plagues, wars, and royal deaths. These entries were descriptive but non-explanatory. A meteor might be described as bright as the moon or as leaving a trail, but there was no attempt to collect the object or analyze its path. The visual experience was recorded, but no empirical connection was made between what was seen in the sky and any object that might have reached the ground. The breakthrough came in the 17th and 18th centuries, in scientific instruments, and methods were applied to celestial observation. Tycho Brahe's observations of the Great Comet of 1577 showed that it moved beyond the orbit of the moon. Challenging the Aristotelian model, he measured its parallax and found it too small. To be atmospheric, he placed the comet in the realm of celestial motion. Johannes Kepler's later work on planetary orbits reinforced the idea that comets were not just fiery vapors, but physical bodies with trajectories. Despite this progress, the idea of falling stones from space was still met with skepticism. The German physicist Ernst Chladni published a treatise arguing that meteorites were extraterrestrial in origin. He cited historical reports and physical characteristics of known stones. His work was dismissed by many at the time. It contradicted both classical physics and Enlightenment sensibilities, which favored terrestrial explanations. However, mounting evidence forced a reevaluation. A turning point occurred in 1803. When thousands of stones fell near L'Aigle in Normandy, France, the fall was witnessed by multiple observers and investigated by the French Academy of Sciences. Chemist Jean-Baptiste Biot examined the site, collected samples, and published a report confirming the extraterrestrial origin of the stones. Their composition included high levels of nickel and iron, and their distribution on the ground matched eyewitness accounts of a single explosive airburst. This event provided the empirical link between observed fireballs and recovered material. It confirmed that objects from beyond the Earth's atmosphere could reach the surface, intact or fragmented. From this point forward, meteorites were increasingly studied as geological specimens. Laboratories in Europe began cataloging their mineral content, structure, and magnetic properties. The word meteorite itself became standard to describe these objects. The scientific community gradually accepted that at least some meteors were caused by solid bodies moving through space and surviving atmospheric entry. This marked the end of symbolical interpretations and the beginning of empirical investigation. No. Ancient civilization had independently reached this conclusion. The tools and frameworks required did not exist. Anaxagoras had guessed correctly, but his reasoning lacked evidence. Most cultures had preserved detailed observations of celestial events, but they had been interpreted through existing cosmological or religious models. Even in cases where a stone had been recovered, as with the Agospatami meteorite, it was treated as sacred, not as data. The transition from symbolic to scientific understanding of meteors, asteroids, and comets required the convergence of mathematics, physics, and instrumentation. Once these tools were in place, the objects could be studied, classified, and explained. The final collapse of the Aristotelian cosmology opened the path to the modern model in which celestial bodies were not signs, but sources of information, and in some cases, potential threats. In modern astronomy, meteors, meteorites, asteroids, and comets are classified based on their composition, behavior, and position within the solar system. A meteoroid is a small, rocky, or metallic body in space. If it enters Earth's atmosphere, it becomes a meteor. If it survives atmospheric entry and reaches the ground, it is called a meteorite. Asteroids are larger rocky bodies that orbit the Sun, mostly between Mars and Jupiter. Comets are icy bodies originating from the outer regions of the solar system, primarily the Kuiper Belt and Oort cloud. These definitions are standardized across, commonly referred to as a shooting star is typically no larger than a grain of sand. These meteors enter Earth's atmosphere at speeds ranging from 11 to 72 kilometers per second. Due to their high velocity, they rapidly compress the air in front of them, causing temperatures to rise and the particle to incandesce. The result is a brief, bright light that typically lasts less than a second. The vast majority of these objects vaporize entirely before reaching the ground. Only a small percentage become meteorites. Meteorites are classified into three main types: stony iron and stony iron. Stony meteorites, which are the most common, are composed primarily of silicate minerals. Iron meteorites are composed mostly of metallic iron nickel and are derived from the cores of differentiated parent bodies. Stony iron meteorites contain significant amounts of both silicates and metal. Many meteorites, especially the primitive carbonaceous chondrites, contain material that predates Earth. Some samples have been dated to over 4.5 billion years, making them some of the oldest matter available for study. Asteroids vary widely in size, shape, and composition. The largest series is 940 kilometers in diameter and classified as a dwarf planet. Most asteroids reside in the main belt between Mars and Jupiter, though populations also exist in near-Earth space and in Jupiter's Trojan regions. These bodies are remnants from the early solar system that never formed into a planet due to the gravitational influence of Jupiter. Some asteroids are monolithic, while others are rubble piles loosely held together by gravity. Their surfaces are often covered in regolith, a layer of broken rock and dust formed by impacts. Comets originate from the colder regions of the solar system. Short-period comets typically come from the Kuiper Belt and have orbits that last less than 200 years. Long-period comets originate in the Oort cloud and may take thousands of years to complete one orbit. Comets are composed of ice, dust, and rocky material. As they approach the Sun, their ices sublimate and release gas and dust, forming a visible coma and one or more tails. The ion tail always points directly away from the Sun due to the solar wind, while the dust tail follows the orbital path. The presence of a tail is the distinguishing feature of a comet, separating it from inert asteroids. The idea that comets and asteroids could be hazardous emerged gradually. In 1980, physicist Luis Alvarez and his son, geologist Walter Alvarez, proposed that a large asteroid impact caused the Cretaceous-Paleogene extinction event 66 million years ago. They based this hypothesis on the discovery of a global layer of sediment rich in iridium, a metal rare on Earth but common in asteroids. The later discovery of the Chicxulub crater in the Yucatan Peninsula supported the theory. The impactor was estimated to be 10 to 15 kilometers in diameter. The resulting energy release caused global fires, atmospheric cooling, and the collapse of ecosystems. This event remains the strongest evidence linking asteroid impact to mass extinction. Further evidence of large impacts includes craters such as Vredefort in South Africa, which measures 300 kilometers in diameter and dates to over 2 billion years ago, and Sudbury in Canada, which is over 1.8 billion years old. These impact structures confirm that asteroid and comet collisions are not rare over geological timescales. In 1908, a comet or asteroid fragment exploded in the atmosphere above Tunguska, Siberia. The explosion flattened over 2,000 square kilometers of forest. The object did not reach the ground. but the airburst was equivalent in energy to a 10 to 15 megaton nuclear device. The Chelyabinsk event in 2013 provided further data. Russia exploded at an altitude of about 30 kilometers. The shockwave injured over 1,000 people and damaged thousands of buildings. Fragments were recovered from a nearby lake. The event was captured by widespread dashboard camera footage, providing detailed trajectory and explosion data. It reinforced the importance of monitoring near-Earth objects. As of 2025, astronomers have cataloged over 32,000 near-Earth objects (NEOs). These include asteroids and comets with orbits that bring them within 1.3 astronomical units of the Sun. Of these, several hundred are classified as potentially hazardous asteroids, those over 140 meters in diameter, with a possibility of impacting Earth in the future. Surveys like Pan-STARRS, the Catalina Sky Survey, and NEOS continue to track and catalog these bodies. The goal is to identify and characterize threats early enough for mitigation. Efforts to counter impact risks have moved from theory to practice. In 2022, NASA's Double Asteroid Redirection Test, DART successfully altered the orbit of Dimorphos, a small moonlet orbiting the asteroid Didymos. The spacecraft collided with Dimorphos at 6.6 kilometers per second. Ground-based and space-based observations confirmed a measurable change in the moonlet's orbital period. The mission marked the first time humans intentionally altered the trajectory of a celestial body. Future planetary defense strategies include gravity tractors, NUCLEAR deflection, and laser ablation. These methods aim to provide additional options, depending on the size, composition, and lead time of a potential threat. International cooperation through agencies like the European Space Agency and the United Nations Office for Outer Space Affairs has increased since the 2010s. The consensus among planetary scientists is that large impacts are low probability, high consequence events. Continued monitoring and preparedness are essential. Modern understanding of meteors. These objects are no longer signs or symbols. They're physical entities with trajectories, compositions, and consequences. They are studied not only for their threat potential, but also for their ability to inform the history of the solar system. Some may carry organic compounds or water-bearing minerals that reveal conditions in the early solar nebula. Regardless of their origin, they are now understood as part of a shared solar environment, sometimes dangerous, often informative, and entirely natural.